As I said, in case you just write an email to me, and even for some exercises that you find, well, not correct or, well, difficult, or you need some clarification. Okay, so today we are going to review basically the application of what we did so far to LP spaces.
Professor, we can't hear you.
Pardon? You cannot hear me? Why? Why?
I can hear, but I'm not sure the others.
Can you hear me now?
Yes, we can hear you. Can you hear us?
Yeah.
We still can't hear you.
So what's the problem? You cannot hear me before? Okay, so what I want just to say is that please, you are welcome if you write me any email for clarification request, and even in case if you want to talk with me directly via Skype or any other platform you prefer. Okay, so today we see the application of, partial application of our theory to LP spaces. And I see that you have already done something in the course of real analysis. So, well, maybe we skip whenever you know some result, just to go to the other part, which is more interesting. So, okay, so this part you for sure know, which is sorry, today I need that, since I need a line, so I will hold this guy over here. So you have a measure space, okay, which is omega, and then the sigma algebra M and me. Like, oh, okay, so this is the space, the sigma algebra, and the measure. And the first assumption is that it's sigma finite, which means, well, you know what does it mean? What does sigma finite mean?
Yes, we know.
Pardon?
Yes, we know.
You know. And you know why it's so important?
Importance.
Well, because there are sigma, well, because a lot of theorems, or many theorems, they work in sets with finite measure.
Yes. Yes, that theorem can be extended to.
And then you have the property, the sigma DTV of the measure. Okay, so I'm going to use some results of the monotone convergence, you know.
Yes, we know.
The Beg dominate convergence theorem, you know.
Yes.
Patou's lemma, you know. Well, it's not the correct way of let's say the time direction is not the correct one. Okay. And then, for example, you know the density of the continuous and compact functions into, I don't know, the
LP space.
Yeah, L1 and, for example, in integrable space, integrable function.
Which integrable? Riemann integrable?
No. Just Lebesgue integral. The fact that the Lebesgue the Lebesgue integral exists, so it's a positive functions. So in L1, you know, and you know Fubini-Tonelli.
Yes, we study.
And you know Radon-Nikodym.
Yes.
Okay, and then at the end, the hand decomposition, whatever. Okay.
Yes, for measure decomposition.
Yeah, the hand decomposition, we measure the positive and negative part. Okay, so definition of LP space. This was not correct, but okay. So it all is the set of functions, okay, from omega into, okay, here immediately we are a little bit in trouble because this should be the equivalent classes. But since we are using real numbers, real vector spaces, we take in R, otherwise, okay. Such that the integral of f to the p, mi, is less than plus infinity. And I will do something which is not correct here. I mean, it can be made correct. So here I will just confuse among functions and equivalent classes.
Just factor construct was this factor space, this one. Just LP. Factor space with respect to what?
Is factor space?
Yes. Equivalence class just almost equality is just.
You call factor, but it's the quotient, no?
Yes, quotient, yes.
Indeed, okay, more precisely, because I consider this is not really related to functional analysis, it's just related to measure theory. So you should have, the one above should be LP, is the one above. Then you say that F is equivalent to G if F, okay, the measure with set F is different than G is equal to 0, and then LP is over this quotient. So identify two functions is the. So I will not do that because, okay, I think everything works. So we will just be a little bit sloppy here and confuse the two facts. In some cases, you need to have a pointwise value. Then you have to be careful. But in general, no. It's just, I mean, in the analysis we do, since we look at as a Banach space, so the dual, and it will always have an integral there, nothing changes. Okay, this is for P, this is for P, 1 infinity, and then you can have for P equal to infinity, you say that the norm of F, okay, I said just the norm of F, let's say the essential supremum of F is less than plus infinity, where the essential supremum is what? Is the, well, there are several ways, so is the, okay, have you seen this notation or? So it is the infimum of all lambda such that the measure of f greater than lambda is equal to 0, and vice versa is the supremum of all lambda such that the measure of f larger than lambda is greater than 0. Okay, so now let's see some theorem, probably you know. Holder inequality. So, okay, and the thing is that the integral of fg is less or equal, mi is less or equal than the norm of f. Oh, sorry, I forgot to say that this thing here is called the norm. So definition, so norm of f, these jokes, they don't work. Norm of f, p to the p is the integral of fp, and norm of f infinity is the essential supremum. So this is for p between 1 and infinity, and for p equal to infinity. for p between, for p less than 1, what you get, well, you get an object that we are not studying in this lecture, in these lectures, and the problem is that you don't have a convex space. So you have a metric, but it's not, the unit ball is not convex. Okay, so now we have the thing, norm of Fp, norm of Gp prime, with the convex relation is equal to 1. Okay, do you notice statement?
Yes, it's just implied by Young's inequality.
Yeah. I just wonder if people knows here.
Yes.
Okay, so we can go on. Remark that you can deduce by this one. So the integral of the product of Fi less or equal than the product of the norm Fi alpha, we'll say Pi, with the property sum over I 1 over Pi equal to 1, which is a generalization. Okay?
Is the product finite?
You notice?
Yes, it's just corollary.
Yeah, it's just a corollary because you iterate as
Yes.
much as you can this guy, and then the exponent, they satisfy this relation. And then the product, the norm of F, okay, what I say, in R is less or equal norm of F, in P, norm of F, P prime, alpha 1 minus alpha with the relation alpha 1 minus alpha 1 over R.
Yes.
So the convexity relation. And also this one is obtained by the Holder inequality. You just here you have F to the power R, and then you use this relation here to write as the product of two functions, then apply Holder, and the exponent will match. Okay, so theorem now. Nothing difficult. The norm, which I call norm, is a norm. You know this?
Yes, Minkowski inequality.
Is because, it's a corollary of this guy again. Theorem, and we got this here, and LP is Banach. So it is complete. And you notice, maybe this started to be a little bit subtle. It's not that straightforward. Yes or no? I don't know.
Yes.
You did the last
Real analysis, yes, we had studied. Yeah, all LP is Banach space. L infinity also Banach space.
yeah, L infinity, it's much easier to prove. In LP, you need a little bit more effort because you need to have essentially obtained a corollary, which is this Fn converge to F in LP. Then there exists Fnk, a subsequence converging to F almost everywhere. Okay? And moreover, well, okay, okay, let's say, and Fn k are uniformly bounded. Function is in LP. Okay, so this is to prove that it is a Banach, if you remember, you need to, so you have a Cauchy sequence, and now you select a sequence such that the sum of the difference in norm converges. No? Then the sum of the norms of the modulus gives you the function h, and since now you have that the sum of the norm converges, well, it means that this is the selected sequence. Okay, so far so good. Let's go on. This I call the theorem. Theorem LP for 1 infinity is reflexive. Okay, there are several proofs of this fact, and so one proof is directly to pass through L2, and in this case, so essentially you prove that the dual of LP is LP prime for P between 1 and infinity, and then the duality relation concludes the stuff. So now the proof of the proof of the book is to show that you have how to say that it is well, uniformly convex. Proof show the uniform that they, okay, at least one part because if you remember, we have seen on Friday that if it is uniformly convex, what happened is that, well, we showed that the canonical injection into the B dual is surjective. That was the proof. Okay, so let's see this proof. I have to say that I don't like too much this proof, but okay, I wanted to stick with the book because I didn't have time. It's not the nicest book, the nicest proof. So, so the first observation, so is very well. Let's copy it. I'm definitely not fond of it, but so first step is that you observe. So you need an inequality on real numbers. That alpha to the power p plus beta to the power p is less than alpha squared plus beta squared to the power p half. Okay, and this is an exercise. Then deduce that a plus b half to the power p, a minus b half to the power p, because at the end we have to get f minus g is less or equal than 1/2. Okay, we just put alpha and beta, so it is a plus b half squared, a minus b half squared to the p half. Then if we compute, this is so it is a squared plus b squared half and now we use the fact that for p greater or equal than 2, so this is an exponent which is larger than 1, so it is subadditive, superadditive, so it's less or equal than 1/2 a to the p, well, it is convex, b to the p. So integrating, finally, we replace f and b with two functions. So when I integrate in this guy, I get f plus g p to the p, plus now I integrate this guy with a is equal to f, b is equal to g, f minus g p to the p, less or equal than 1/2 f p to the p, 1/2 g p to the p. And this is the uniformly convex. Okay? Because if f equal to 1, we discover that f plus g half so now you get 1 minus so whenever this distance is larger than some epsilon, this is less than y minus that epsilon to the p divided 2 to the p. Okay, so this is the uniformly convex. LP is uniform convex. Okay, this is the first step. So now we know that it is reflexive. So now the second step is to prove then what is the dual. So if now is 1 and 2, define, okay, now we are going to prove that the dual of LP with P1 between 1 and 2 is exactly the reflexive space. So define, consider, let's say, U, which is a function now in LP, and maps to the dual, let's say the functional f of u, which belongs to the dual of LP star, LP prime star, 1 over p plus 1 over p prime equal to 1, and with the property fug is equal to the integral of f of ug, okay, which is perfectly defined because of Holder. So the map is okay because of Holder, because it tells me that, well, actually, the norm of U will be less than the original norm. So indeed, okay, this is written, so is less or equal than U P prime, P F P prime. Okay, so the norm of F of, the norm of this guy here, sorry, this was G, as a functional in LP prime dual is less or equal than the norm of U, P. Okay, so now let's prove that instead you have an equality. Here I can remove. so let's take G. Is equal to u to the p minus 2. And then you can verify that G, the norm of G, okay, in the p prime is less than infinity. Okay, we can compute it, and this is exactly, so it's the integral u to the p minus 1 divided times p prime, and p prime is p divided p minus 1. So it's equal to the norm of u p elevated to the 1 minus p. So it's p over p prime, the computation. Okay, let's study now what happened there. So the integral with this particular G is the integral of u to the p to the p. On the other hand, this should be less or equal. Okay, and then if you apply this property, so this is equal to what? Norm of u, norm of u to the p. And here we get, should be p minus 1, and p minus 1 is exactly this exponent here. Okay? So norm of u, norm of g, and both of these equalities implies that the norm of f of u is equal to the norm of u. So the norm of f of u in the dual is equal to the norm of u in the primary. Okay, I'm just saying that I've almost identified the space. I don't need it right now, because I conclude for this proof. Indeed, it is not nice because you need two steps. So u maps to f of u is a closed subspace of LP prime star. But now we know that this is reflexive, the dual is reflexive, closed subspace is reflexive, which means that LP 1, 2 is reflexive. Okay, so the proof is not very nice, because at the end, the dual of LP is exactly LP prime. So let's review the proof. The proof is that for the case P larger than 2 is immediate by, well, an inequality in R. This is the convexity of a function 1 plus alpha to the P, more or less. For the case P between 1 and 2, well, you prove that by the Holder inequality and choosing particular function, that it is a closed subset. So it is, well, it can be considered or embedded isometrically and linearly as a closed subspace of the dual of LP prime. Well, P prime now is between 2 and infinity. Then you deduce that it is reflexive. Okay, and indeed the next theorem is Reith Theorem, which is that the dual spaces are the same. So let's write it this way. LP prime star is equal to LP between, okay, And now, let's say, I already write depending on, okay, this is 1p and infinity. So we do this case, then we will discover that if p prime is equal to 1, the dual is L infinity. Well, and the thing is already here. So suppose not. Oh, it's here. Okay, that embedding there, u maps to f of u, is not surjective. Because we know from here, okay, this reasoning does not depend on p, even if we do for p equal to between 1 and 2, it works for all p. So suppose it is not, now we know that it is an isometry, so it is a closed subspace, which means what? It means that LP, let's say LP is closed subspace of LP prime star, and then if it is not surjective and there exists, so they are reflexive here, there exists, let's say, a G in LP prime such that, I'm sorry, I have really to cancel what I need the inequality here. Such that G u is equal to 0 for all u belonging to, there is a G in L, so it's for all u belonging, sorry, is the dual, I go in LP, so there exists a point in LP such that is not 0 for all u belonging in LP prime. Sorry, LP, no, there exists in a function in LP prime, in LP prime, such that, because I'm embedding LP in LP prime, such that for all u in LP, so the image of this map is not the whole space, so there exists, being reflexive, a vector in the original space separating the closed subspace, which is this closed subspace, from the rest. And the vector is non-zero. But now let's look at this trivial scaling. So if now u, okay, I take the one which is in the front. So it is G p minus 2. So it's p prime and then p prime minus 2. Then this u belongs to LP, and if I do the computation, the integral of G u is equal, okay, is the computation done here, so it is the norm of G in LP prime. But being 0, I get that this is 0. So it is a contradiction. Okay, so this is for the good case. And another thing that I forgot to say here, let me put here. Well, I said it is an isometry, so this is isometry. In this sense, so the norm is really the same. Okay, and now another result, which is due to depends on what you know, so let me put it here. proposition. So I consider it finite dimensional. I don't want to write something. Okay, yes, it does not in the whole generality, just in R. So in Rn, dense in Lp of Rn for P, 1 and infinity. You notice result? The result in measure theory is not a result in LP spaces.
Yes, we used it. We used this statement several times in solving problems.
Yeah, because it essentially is the property that the measure of a set, okay, any set can be approximated by in L1 by functions which are continuous and compact. Okay. So indeed this is a statement. I would say it is a statement about the topological properties and the sigma algebra. Okay, the topological properties. It's not a statement about LP. Now another theorem. So well, do I do that? Okay. Okay, if the sigma algebra M is countably generated, then LP is separable. As usual, 1 and never infinity. Infinity is not too strong. Okay, you notice the result there. So you know what does it mean countably generated?
No?
Okay, so it means that the sigma algebra, so M is countably generated. Somebody call it separable. Separable depends on the text. If there exist countably many sets, let's say omega n, generating M. So, for example, in Rn is certainly countably generated because the topology which generates the sigma algebra has a countable base. Okay, so, and why then LP is separable now? Let's sketch the proof, because these are results in measure theory, not results in proof. Okay, since the sigma algebra is countably generated, I'm saying that, okay, so the main observation is that every okay, so let's see, okay, there exists countably many set in the sigma algebra such that, okay, such that, let's say, the inf over n of the measure of the difference for all A in the sigma algebra M. Have you seen a statement like this one? So if this count be generated, well, it means that you need just to have the algebra generated by the AN, and they approximate all the sets in the sigma algebra. But this is important to notice that I'm here using the fact that it is sigma finite, otherwise it's not true. It's important to be sigma finite, because I do encompass it. Okay, and then once I have this guy, which is an exercise, how to conclude? Well, now I can approximate, so with countable minisets, so I deduce that every simple functions can be approximated by, but I should say the same statement there. So there exists a countable family here, let me say here, well, me is finite. So, because otherwise I need to, let's do for finite thing, otherwise I need the approximate. So there is a countable family of simple functions approximating any simple function. Okay, because if I can approximate sets, I take the simple functions using only the sets AN with rational numbers. So there are countably many simple functions which approximate all my simple functions. So finally, well, so for any function in LP, there exists a simple function living in a set of finite measure which approximate as much as I want. So simple functions are dense in LP. Then what I obtain that, okay, so I have an approximation whose LP integral I can require to be as small as I want. Not only one, even LP, because at the end my simple functions, they differ only on the sides of the height, and which is a parameter which I can make as small as I want. And finally, okay, I'm not very, it's the sketch of the proof simply because it's not a result related to LP space. It's the result of measure theory. So are you familiar with reasoning like this way? I think this is the part of real analysis, more or less. So now we have, for P, 1 infinity, we have everything. So we know separability, and we know the reflexivity. So now we study L1. Okay, maybe you know also the theorem is the dual of L1 can be identified with L infinity. Okay, you know this theorem, or well. Okay, my impression is so my feeling, let me say, is that the proof that I'm giving now is a proof which can be applied also to obtain the reflexivity if you know that L2 is reflexive. Because the one that maybe is the easiest, I don't know, is to prove that L2 is reflexive, and L2 is reflexive because it's a Hilbert space. And Hilbert spaces are reflexive. Or if you can stick with the proof here, for Hilbert space, the convexity, the uniform convexity is automatic because you have, I mean, you have the parallelogram inequality, so it's much easier. So here what I do now, I make some observations. First of all, so we assume that omega, the measure of omega, is, let's say, finite. So we are sticking one of these omega n, let's say, let me call it here, so omega is equal to the union of omega n and the measure of omega n less than infinity. Then what I do now? Then, by Holder inequality, so what is, not by Holder, sorry. This is not the smart thing. So by Jensen, the integral of u to the p over omega, one of these omega. Okay, this is less or equal than, okay, I should normalize, so it's 1 over the measure times is the measure of omega, the integral of u to the p. So it is less than plus infinity. So I conclude that L1 in this omega is contained in LP of omega for all p. Sorry. No, it's the opposite, sorry. Sorry, it's the opposite. It's LP of omega is larger or equal by Jensen. Then it's Monday. So the average is 1 over, so it is the measure of omega. And then I have the integral 1 over the measure of omega of u to the p. Okay, and now it's correct. So p minus 1, sorry, 1 minus p, the integral of u. Me. Okay, so I discovered the following. I discovered that if I'm in LP, it's embedded in L1. So LP omega is contained in L1 omega. If omega has finite measure, no? So why I need this estimate, for example, L2? Simply because for LP I know already what is the dual. So because now I have an estimate on the norm, so what does it mean? It means that the dual of LP star contains the dual of L1. because any dual function here can be considered as a linear functional over LP. So I deduce, from this I deduce there exists, so for every, let's say, linear functional psi L1 star, there exists a function G in LP star such that the integral GU is psi U. So this is my previous representation. So, and indeed I need just for one space to be able to have the representation. Okay. So now the problem is that G is a function defined on U. So so G cannot be so the problem is now what is the property of G? Because then I know, so this G, so G is defined. I know the following: GU is less or equal than some constant, say M, norm of U in L1. So now my problem is I have a function which represents the linear functional over, well, at least some subspace, which is the LP, and I wonder now if what is the requirement in order to represent the linear function in L1. Then you observe, so, well, this is a verification. So one verify that G must belong to L1. So what I said that, well, this functional is represented by the functional in LP. But not all functions in LP star are good, because I must require this additional relation, which is the relation that it is in the dual. So I have a functional, so I obtain the representation for free, but how to force to be the dual? I need to require that this holds. And this holds only if it is in L infinity. Why is that so? Indeed, if, okay, we take, let's say, if lambda is less than the essential supremum of G, take U equal to the sine of G, the characteristic function of lambda. Let's say of G greater than lambda, which is the proof that I have here, which I cannot make it work simply because P is not, I mean, when I compute the exponent, I get an infinity or a 0. So let's compute now what is the integral GU. So it's the integral over this set. And what I get is exactly modulus of G. So, and this is larger than, by definition, lambda, the measure of the set. But the measure of this set is the norm L1 of U. So I discovered that the norm of this operator so the norm of, this operator G in the norm, in the dual norm, is equal to the norm of G infinity. Okay, so for finite sets, everything is fine, simply because I can use this embedding. So what about infinite sets? For infinite sets, you conclude by just making the partition. And we take the omega n disjoint by simplicity. That doesn't matter. So let me put here disjoint. Just for free. Then U is the sum of U restricted to of times the characteristic function of omega n. So it's the sum of Un. And I'm saying that this is converging in norm. So the definition is perfect because it's a series which is converging. It's a Cauchy sequence, or it is a series which is converging. And simply because U is equal to 1. Then now, so now what I have, hence, if psi U being continuous is the sum of psi Un, because psi is a continuous functional, but each of these is the sum of the integral of G Un, so now in the set omega in. And now I have the property. So the fact that this is bounded implies that the norm is uniformly bounded. This guy is in L1, and then I can use the Beg Convergence Theorem, and this is equal to the integral of Gu. So Gn, let's say Gn, where G is defined by G is the sum Gn restricted to the set omega n. So it's straightforward, and if you want to play a little bit, inside this proof there is always the reflexivity proof. We're starting with just one element, which is L2. Now you have the embedding for, let's say, P larger than 2 goes into L2, and then you have the representation, and then you obtain that LP. You obtain the duality. I have to say that I prefer this proof. I don't know why I stick with the book, because it would have been much easier, but okay, we stay here. Okay, so now let's make a remark about the reflexivity. So L1 is, unless it is finite dimensional, when it is just RD, is never reflexive. Let's say if infinite dimensional.
Because L infinity is not separable.
L infinity is not separable. Yeah, we will see later. And even here is the case that if it is infinite dimensional, is not separable. Okay, so why is not infinite dimensional? So there are two cases. So one case is that, well, if the sigma algebra is purely atomic, okay, then the dual is L, we will see later, then the dual, okay, I don't know if to do it now or later. then the dual. Okay, then this is isomorphic to L1, at least some subset. And what? So if you have countable many atoms, essentially it's something like to take L1. At least a subset of the whole
What is an atom?
space. Now the dual of L1, we have already the proof, is L infinity. L infinity is non-separable because L infinity so contains the power set of n and the distance of A, B in any subset of n with A different than B. So you have the distance is the L infinity distance is always 1. They have at least to switch in one point. So you have uncountably many sets, because the power set is uncountable, whose distance is 1 cannot be separable, no? Trivially, because otherwise, I mean, you need to have uncountably many points inside each of the ball of a radius 1/2. Okay, this is the stupid part. The other part is when omega, let's say, as a continuous part. Jokes are bad. I'm sorry. They are very hard. So for all epsilon, there exists omega, or for all n, omega n less than 2 to the minus n. So you have some continuous part. Then set. Okay, now what we do, the characteristic function of omega n divided by the measure of omega n. And so this is a sequence of functions in the unit ball. In the ball of L1, centered in 0, radius 1, closed. So if it is reflexive, it should converge weakly. But the dual being L infinity, okay, now, so they should converge to a function. So if Fn converges to G, now the support has measure 0. And on the other hand, you can say that so they should converge to 0, but actually if you take, okay, that is the integral of Fn is equal to 1. So you get a contradiction because the integral is with the function g, the function in the dual constant equal to 1. So it should be 1. On the other hand, the support is 0, which is a contradiction. Indeed, they converge, well, in some space, they converge to distribution. That's it. Study of L infinity now. So L1 is done. And then L infinity, and then we make this, we sum up a little bit what we have here. Infinity is non-separable. Let's start with this guy. very bad. Okay. So the proof is inside here. So if the cardinality, well, the cardinality, so it means how many different sets you may have. So different up to set of measure 0. So if there exists, so let's say if, okay, let's do the proof in, okay, if there exists a family omega I intersection omega j is empty, and the measure of omega I is greater than 0. Then we define a particular, essentially we define the set of function g in L infinity, and g is defined like sum of what? Of alpha I characteristic function of omega I, where alpha I belongs to, well, so is a partition. So alpha I is in L infinity, let's say alpha I is 0, 1 for all I. So essentially I'm saying that this is what, if you give me so for every A, which is AI, which is in the power set of n, I can associate uniquely a function g, which is the sum of AI omega I. And now, if you go back here, well, what happened? It happened that the distance, the L infinity distance of these sets is always 1, because they differ by 1 in a set of positive measures. So the thing is exactly the same as here. And so, in particular, there are functionals which are not in L1. Over infinity, you have functions which are not in L1. Okay, so let's do some example here. In particular, there are functionals which are not in L1. Okay, let's do some example. Okay, let's start with here. So define the function f associated with the t times 1, 1, so the sequence of 1 equal to t. So it is the limit function. Okay? So I extend a little bit more, so I define the function f like, so let's do the following. This is not, because I cannot solve, so I define f, which is defined on every sequence which is the limit of g of gn for every g belonging to L infinity who has a limit. this is defined in a linear subspace of F. So F of L infinity. F is defined on a linear subspace of F. And actually, okay, actually it's even in a closed subspace because the limit is continuous compared to the C0 norm, but okay. So what happened, moreover, is that Fg, so F is linear. That's trivial because the limit is, the linearity is continuous. So the Fg is less or equal than norm of G. Clearly, because by definition of an infinity norm. So there exists an extension which we call lim, which maps L infinity into R, which extend the limit function. By Hanbana, I have an extension. Lim is not 0, no? Lim, for example, the lim of 1, 1, 1, 1, 1 is equal to 1. So lim is not 0. But for all f in L1, lim of f is equal to 0. Okay, so lim is a function which separates, well, is separated from the space L1 by, for example, this vector in L infinity.
Professor, I think the definition of this capital F is that Fg equal to lim Gn, G belongs to C, little c. C is a set of space of convergence sequence.
C?
The definition of Fg, F of G. G belongs to small s.
It's continuous because in the limit, yes, if you say that it is continuous function, it means that you have a limit for infinity.
And, yes.
It depends. I say, because usually I say, I don't, well, it's the fact that continuous over n are the function who has a limit.
Yes.
Yeah, okay. Usually, because I usually use this C0 and C compact. C0 is the limit 0. But okay, you can...
But in the definition, for any in L infinity, this limit may be non-exist because it's just bounded. We have not any information about limit.
No, we don't have a, no, about this function, no, you don't have any unique extension.
Yes, but in the definition of large f, the starting point, G belongs to small c, not L infinity.
L infinity who has a limit. If the limit exists, I say that the function is equal to the limit.
Ah, yes, okay, then it belongs to small c.
Yeah,
Yes.
and then I extend uniquely.
Yes, thank you.
Okay, and what about the dual? So the dual is interesting, but I'm not doing to, because the dual is, well, the dual is completely a strange thing. And, okay, I put some notes, but I think there is no time, so let's forget. In any case, you can have a representation of the dual space, and you use the fact that L infinity is an algebra, and so it's a Banach algebra actually, and so you can use the representation of the linear homomorphism of L infinity into R. But okay, we can stick there. Done, this is done, this is done. Okay, so let's make the map now. So this is P equal to 1, P between 1 and infinity, and then p equal to infinity. So let's put with separability. So yes, yes, no. I mean, well, there are some cases where it is yes, but in the standard case, which our example is Rn, this is the situation, no? So dual, reflexive, so no, and yes, no. So the duality is L infinity, LP prime, and okay, this is
S of K, some compact space for some compact space.
this is the dual of some of the continuous. They are measures on some compact set, and the compact set is the space of homomorphism over the convex set. Okay, here there is some space, so it's continuous. Sorry, it is the measure over some compact space, and the compact space, however, is not cannot be metrized, so it's a bad situation. It's not a nice space. Duality and parallel reflexes, duality, and whatever. I think we have all. Okay, so this is basically the picture to have in mind. Okay, so now let's start with another subject, which is the regularization. So we know that the continuous functions are dense, but now let's live in Rn, where we have also C infinity functions, and regularization, convolution. Okay, convolution. So the main object here is the properties of convolution. So let me say what is a convolution. So we have F, which is in L1, and from now on we live in Rn, and G in LP of Rn, and P 1 infinity, even infinity here I'm allowing. Define. If it exists a new function, which is f convoluted g, this is the new function, evaluated in x is equal, if it exists, fx minus y, gy, dy. So the nice property of convolution is that when you do the Fourier transform, it becomes the product. Here we are using for other thing. Now the proposition is that, well, for almost every x this is defined. Almost of x, and well, in this case is Lebesgue, sorry. Lebesgue and almost every x, and its norm.
Professor?
Yeah.
What is the motivation for convolution?
Okay, the motivation for convolution that we see now here, sorry, I forgot the call. The motivation for convolution that we see here is a regularization effect. Because if you look at this guy and imagine f to be very regular, so it's just, instead of the integral, it's just a sum, weighted sum, and then you see that is a weighted sum of function which is as regular as I want. So the idea is that in this way you are going to regularize the function g. This is the way we are using in these lectures. But the motivation is much more because the Fourier transform of this guy is the product of the Fourier transforms. Something like, well, we didn't see that. I don't know if the exercise you have the info convolution. Probably, I think one exercise was about the info convolution of two convex functions. So the Legendre transform of the inf convolution is the sum. And so it's very nice because you know how to transform sums, or vice versa, you know how to obtain properties or regularization property. For example, if you want to have an approximation, then you take your functions and then you add a small ball, and then in the rest you get some regularization. So, and here the thing is that, so if you ask what is the transform of a sum, the Fourier transform of a sum of two functions is the convolution of the transform, or should be with the minus, there is some sign because it's involutive, the Fourier transform, but we are not going to that. In any case, the convolution is very important, and just to remember, if you see, or if f is the Fourier transform, so maybe it's better if I write something. I hope somebody is going to show you the Fourier transform. So the Fourier transform of a function f is by definition, okay, I need some normalization here. So 2 pi I e to the xi dot x. Okay, let's do in the scalar case f of x dx. Now the property of convolution is the Fourier transform of the convolution is the product. Okay, so this is a very important property. And if you think, well, a lot can be explained also. Also, the theory that I'm doing now can be explained by using this property. If we want to be, to see everything from a more general level. So far, what I'm interested is to use the convolution as a tool to build nice approximations. So here, convolution is a tool to build nice approximations. That's it. We are not going to exploit all the stuff. Okay, so let's prove now the proposition. But even this one is basically a theorem of measure theory. Let's hope to finish in time. So now I split, this is my feeling, because when so now I want to show that for almost every x, this object is integrable. So I get at least this value. So write the integral of f(x minus y). So, well, I divide into two sets. So gy equal to the integral where gy is less than 1 plus the integral where gy is larger than 1. Okay, this guy, clearly, it exists for all x, no matter what is x, because f in is 1. In L1. Okay, so the problem is this guy over here. But now I observe that if I integrate this guy also in dy dx, so I integrate over all x, let's say I integrate the modulus over g larger than 1. Okay, as a function defined in the whole set. Well, wait a minute. When I integrate in dx, so,
Fubini.
well, I'm using Tonelli.
Ah, okay.
Because I'm using Tonelli, and then I deduce by Fubini. So let's compute by Tonelli. So this is the integral. Okay, you said this is the norm of f. So I say, if I want to be precise, I'm doing the following. I'm integrating g larger than 1, g over all r, and f x minus y dx dy. Okay, this guy is norm of f1. This guy is the integral g dy. But this guy here, being p larger or equal than 1, is less or equal than norm of f1 norm of g p to the power p. Okay, so I obtain that at least this iterated integral is finite. So I deduce by Tonelli, I deduce that g, y, f, x minus y restricted to the set where g is larger than 1, larger or equal, sorry, doesn't matter, larger than 1 is in L1 of the product. Now I use Fubini. By Fubini. By Fubini, if I fix y, if I fix x, the integral of y exists for almost every x. There exists, so let's say f of x minus y gy restricted to the set where g less or equal than 1 is in L1. And now, well, so this guy is defined for almost every x. This guy is defined for every x. The two set are disjoint, hence the function is in L1. Okay? Almost every x, f, x minus y, gy is in L1. Okay? So now let's compute the p norm. So at this point I have a function, I can compute the p norm. Well, but now I can make something easy, no? So if H is the dual, let's compute it. So I integrate, is the double integral, hx f x minus y gy dy. Now I change variables, so it's the integral Now let's call this fz, so let's call this z, and then I have that x is equal to z plus y, gy dy dz. Sorry, here there's dx. And now when I integrate in y, it is less or equal than modulus of f. And here I have this guy which is norm of h, p prime, norm of g, p, dy, no, dz, sorry, dz. And then I get the estimate. Norm of f1, norm of gp, norm of hp prime. And now remember that the LP norm of this guy is the supremum of the norm of the dual. So that's why I need the 1 infinity here. Okay, I can take 1 plus infinity, but then, okay, if it is infinity, it's elementary. So if this infinity is bounded by the L infinity norm, so I just take the other one. So the norm of this guy is the supremum with respect to h. Well, it pours also in L infinity, and this is bounded by this constant here. Okay, so I conclude. And we stop here today. Okay. Are there questions? Not. We will see tomorrow, if I'm not wrong. So it should be tomorrow, yes. Okay, have a good day.
Thank you.
Thank you.